Okay, students, myself Dr. Amit Bikram Patnaik. I will teach you now vectors. So, we know the vectors and scalars in physics. So, vector is a physical quantity which has more than one unit of measurement. So, one is vector and scalars. So, vectors has one unit of measurement. So, vectors are, examples of vectors are force, velocity, and acceleration, etc. And scalars has one unit of measurement, that is mass, length, etc. So, examples of scalars are mass, length, volume, etc. So, how to represent a vector? To represent a vector, we have mentioned its both magnitude and direction. Suppose AB is a vector, we can represent AB by its arrow, that is AB, and it's mentioned by A to B, where A is called as initial point and B as terminal or end point, and it has direction AB vector, and its magnitude is, we can denote it by AB. So, next we come to the types of vectors. So, there are the types of vectors are, so first one is we call as position vector, PV, that is defined as position vector. So, position vector is, if origin is considered to be the initial point, then it's said to be the position vector. Suppose we write down OA vector, and O is initial point and A is terminal point, then we call OA is the position vector of A, and we represent is, suppose that is A vector. So, first one is position vector. Second one, we can say it as null vector. Null vector is defined as zero vector. So, null vector has magnitude 0 and it has arbitrary directions. So, third one is called unit vector. Unit vector is defined as, it has magnitude 1 unity and it has a direction along a vector. Suppose we have a unit vector A cap is defined by A vector divided by magnitude of A vector. So, this is called as unit vector. Next, we have parallel and anti-parallel vectors. Parallel and anti-parallel vectors. So, two vectors, say A vector and B vectors, are parallel if they have the same directions. That is, B vector is said to be parallel to A vector. We can represent B as a scalar multiple of A vector, that is, B is equal to m times A vector, where m is a scalar quantity. M is a scalar quantity. So, B is equal to m times A vector. If m is positive, then you say two vectors are parallel, and if m is negative, for m is positive, that is parallel, and if m is negative, then they are said to be anti-parallel. That is, A vector and B vector, they are parallel, they have same direction, and if they are in opposite direction, they are said to be anti-parallel vectors. So, next we come to vector different operations. So, what are the different operations of vectors? So, one is So there operations of vectors. So one is addition and subtraction. So two vectors can be added or subtracted by parallelogram law of addition. Suppose A vector and B vectors are two vectors. Then we can add these two vectors by the resultant vectors, which is defined as A plus B vector. And by subtraction, it is also by vector operations. Suppose it is minus B vector, then it is defined as A minus B vector. So similarly, two vectors can be added or subtracted, that is addition and subtractions. Next we have the second operations, multiplication by scalar. Second one is suppose A vector is, and we can multiply by a scalar, that will be m times A vector, and mind it, we can never put any dot or cross on it, because in vectors dot and cross has some definitions. So if m is a, where m is a scalar, suppose for example 2 times A vector, that is we multiply 2 with A vector, so this is called as multiplication by scalar. Next, third one is we define as product of two vectors. Product of two vectors. So two vectors can be, product can be defined as, one is called vector or cross product, and other one is scalar or dot product. So vector product and scalar product. So vector product is defined as, in other words, is a cross product. Suppose we have two vectors, A vector and B vector. Its cross product is defined as A cross B vector. We come to next part, that is A cross B vector. It is a vector quantity, and if A and B are two vectors, its scalar product is defined as A dot B vector. So it is a scalar quantity. So take one example. Some examples of scalar products are scalar products are force. Sorry, scalar products. Some examples of scalar product we can define is work is a scalar quantity, is a force and acceleration. So work is a scalar quantity which is defined as F dot S. So it is a scalar product. So similarly, we have vector product, this is momentum, etc. These are vector product. So next we come to how to represent vector geometrically. So in mathematics we have geometrical representation of vectors. So we can come by this geometrical representation of vectors. So first of all we come to two dimension. In two dimension, suppose that is x axis and y axis. Suppose a point is P having coordinate xy. P is a point in two dimension whose coordinate is xy. So how to represent in vectorically? So if O is the initial point, we join OP as its position vector as R vector. Then I cap and j cap are unit vectors along x and y axis. Suppose this part is and this part is x and this quantity is y. So r vector can be represented as xi cap plus yj cap, where x and y are called scalar component of r vector, and xi cap and yj cap are vector component of r vector. So this is in 2 dimension. If we come to 3 dimension, in 3D, this is in 2 dimension. If we come to 3 dimension, 3D, that is in, if we consider 3 different axes, x axis, y axis and z axis, and point P is x, y, z. So OP vector is r vector. Similarly, r vector will be xi cap plus yj cap plus zk cap. Similarly, x, y, z are called scalar component of r vector, and xi cap, yj cap and zk cap are vector component of r vector. Next, we have what is the magnitude of r vector. So magnitude of r vector is defined to be r vector magnitude, that is equal to root over of x square plus y square. So this is a simple case of a right angle triangle. So r is the hypotenuse. So r vector magnitude is equal to x square plus y square. Now the unit vector along r vector is defined as r cap. So r cap is defined to be r vector by magnitude of r vector. So r cap is unit vector along r vector. Similarly, in 3 dimension, we have simply add x square, y square plus z square. So this is geometrical representation of a vector. Next, we find the geometrical. Suppose A and B are 2 points having coordinates x1, y1 and B x2, y2. So this is a line segment AB, and so now the position vector of A vector is defined as OA vector is equal to x1 I cap plus y1 j cap. Similarly, position vector is V vector is defined to be, this is suppose A vector, B vector, OB vector, that is equal to x2 I cap plus y2 j cap. Now AB vector can be found out by a resultant vector, that is OA vector plus B vector is equal to A vector plus AB vector is equal to B vector. Then AB vector is equal to B vector minus A vector. So B vector is defined to is the position vector of B minus position vector of A, that is equal to position vector of B, that is we simply subtract the component wise, that is x2 minus x1 I cap plus y2 minus y1 j cap. So that is AB vector, and x2 minus x1 is called scalar component of AB vector, and y2 minus y1, these two are called scalar component of AB vector, and its vector component are x2 minus x1 I cap plus y2 minus y1 j cap. Now the magnitude of AB vector is defined to be root over of x2 minus x1 whole square plus y2 minus y1 whole square. That is the magnitude of AB vector. Now, if I have unit vector along AB vector, suppose that is AB cap, which is nothing but AB vector divided by magnitude of AB vector. So, that is the unit vector along AB vector. So, this is in 2 dimension. Similarly, in 3 dimension, we can add z coordinate, that is x1, y1, z1 and x2, y2, z2. So, this is the geometrical representation of vectors. We can, in mathematics, we have the geometrical representation of vectors. So, next we come to direction cosines and direction ratios. So, direction cosines and direction ratios of, so direction cosines and direction ratios. In short, we have defined DCS, that is direction cosines, and direction ratios are DRS in short. So, first of all, what is direction cosines? So, direction cosines is, suppose P is a point having coordinate xy and O is the initial point. So, we have OP vector as R vector. Then we draw components M, OM is x and PM is y, and say the angle is theta. So, first of all, you define what is direction cosines. So, direction cosines is nothing but cosine of direction. So, cosines means cos, so that is cos theta. So, cos theta is nothing but y, that is PM by OP. So, which is equal to y by r. So, that is y by r. Similarly, we have direction cosines cos theta. So, what are the direction cosines? So, direction cosines are direction cosines of r vector r, x by r and y by r. So, this is called direction cosines. So, make this brackets. So, direction cosines are x by r and y by r. So, then comes to direction ratios. So, direction ratios are numbers which are proportional to direction cosines. So, direction ratios are numbers which are proportional to direction cosines. So, obviously, direction cosines are direction ratios. So, those which are direction cosines, that is also direction ratios, because direction cosines is proportional, every number is proportional to itself. So, direction cosines are proportional to their number. So, direction ratios of r vectors are also x by r, y by r. So, this is about 2 dimension. Next we come to 3 dimension. So, the same case applied to 3 dimension. In 3 dimension we have axis x axis, y axis and z axis, x, y and z. X axis usually perpendicular to the blackboard, that is away from the blackboard. So, suppose a point P is here and OP is on, O is the initial point, R vector. So, it makes an angle alpha with x axis, beta with y axis and gamma with z axis. So, alpha, beta, gamma are called direction of the lines. So, alpha, beta, gamma are called direction of line. direction of r vector. Then cosine of direction, that is cos alpha, cos beta, cos gamma. So cosine of directions are called direction cosines. So cosine of direction is called direction cosines. So it is, suppose P has coordinate x, y, z. So direction cosines cos alpha is equal to x by r, cos beta is equal to y by r, and cos gamma is equal to z by r. So x by r, y by r, and z by r are called the direction cosines of line, direction cosines of r vector. So direction cosines of r vector is r x by r, y by r, and z by r. So subsequently they are also direction ratios. So direction ratios of r vector is also x by r, y by r, and z by r. So this is all about direction cosines and direction ratios. Next we come some examples. Take an example, that is, suppose A is a point having coordinate 2, -3, 1, and B is coordinate -4, 5, 3. So what is the direction cosines and direction ratios of direction cosines and direction ratios of AB vector? So first of all we find out AB vector. Now subtract the component wise, that is B component minus A component, that is -4 minus 2, 5 minus 3, and 3 minus 1. So AB vector is equal to -6, 8, 2, or we can write it as in a component wise, that is equal to -6 I cap plus 8 j cap plus 2 k cap. So AB vector magnitude is nothing but root over of -6 square plus 8 square plus 2 square, which is nothing but 440 plus 64, that is 104 root over. So direction cosines of AB vector are magnitude of A vector, scalar component of A vector divided by its magnitude, that is -6 by root over of 104, 8 by root over of 104, and 2 by root over of 104. So these are the direction cosines of AB vector. And suppose we have asked the what are direction ratios of AB vector, this same quantity will be direction ratios. So next we come to another example. Suppose we are given 3 vectors, that is A vector that is equal to 2 I cap minus j cap plus 3 k cap, B vector that is I cap plus j cap plus 2 k cap, and C vector is equal to 3 I cap minus 4 j cap plus k cap. So what is unit vector along A vector minus 2B vector plus C vector? So first of all we calculate A vector minus 2B vector plus C vector, that is equal to 2 component wise 2 I cap minus j cap plus 3 k cap minus 2 times I cap plus j cap plus 2 k cap plus 3 I cap minus 4 j cap plus k cap. So it will be 2 minus 2, that is 0, plus 3. So that will equal to 3 I cap. Next minus 1 minus 2, that is minus 3, minus 4, that is minus 7j cap, plus 3 minus 4, that is minus 1, plus 1. So that will be 3i cap minus 7j cap. Next, magnitude of a minus 2b plus c vector is equal to root over of 3 square plus minus 7 square. So that is equal to root over of 58. So unit vector along a minus 2b plus c vector is nothing but a minus 2b plus c vector divided by magnitude of a minus 2b plus c vector. So this is equal to 3i cap minus 7j cap divided by root over of 58. So this is all about unit vector, scalar component, vector component. Next we come to product of two vectors. First we will discuss the scalar product of two vectors, that is dot product or scalar product, dot or scalar product. Suppose we have two vectors, a vector and b vector. Now the product of these two vectors a and b will be in scalar product is defined to be a dot b. So examples of some dot product or scalar product is, one example is work. Work is a scalar quantity which is nothing but force displacement. If it's force and force, F dot S. So this is a scalar product. So similarly, if A and B are two vectors, its scalar product is defined to be A dot B. So A dot B is defined to be A B cos theta, where theta is angle between A vector and B vector. So we can draw like this. Suppose O, it is A vector, is B vector, and angle between A and B is theta. So if we drop a perpendicular, that is BM, and this quantity is B cos theta. So A dot B is equal to AB cos theta, where theta is the angle between A vector and B vector. Now if theta is equal to 0 degree, so cos 0 is 1. So A dot A is A square. A dot A is A square. So A square is a scalar quantity which is nothing but dot product of A and A vector. Next, suppose I cap and j cap. I cap is unit vector along x axis. So I cap dot I cap is 1. J cap dot j cap is 1, and k cap dot k cap is 1. If theta is equal to 90 degree, we have cos 90 is equal to 0. So this is presented by I, j, k, 3 perpendicular. So I dot j is equal to 0, I dot k is equal to 0, j dot k is equal to 0, because I cap is perpendicular to j cap and k cap. So this is represented by 3 vectors I, j, k perpendicular to each other. So if theta is 90 degree, then the dot product will be 0. So I dot I is equal to 0. So if we have defined in a component wise, suppose A vector has component A1 I cap plus A2 j cap plus A3 k cap, and B vector is b1 I cap plus b2 j cap plus b3 k cap. So A dot B will be a1 b1 plus a2 b2 plus a3 b3, because I dot I is equal to 1, j dot j is 1 and k dot k is 1, and I dot j is 0, I dot k is 0, j dot I 0, j dot k is 0. Similarly, so we have A dot B is equal to a1 b1 a2 b2 plus a3 b3. That is component wise we can define A dot B. So take one example. Suppose A vector is equal to 2 I cap minus 3 j cap plus 4 k cap. B vector is equal to I cap plus j cap plus 5 k cap. So what will be A vector dot B vector? So it simply multiply its component, that is 2 into 1 plus minus 3 into 1 plus 4 into 5. So which is equal to 22 minus 3, that is 19. So A dot B is equal to 19. So it is a scalar quantity. Take another example. Suppose A vector is equal to lambda I cap plus 2 j cap plus 3 k cap, and B vector is equal to I cap minus 3 j cap plus 4 k cap. If A vector is perpendicular to B vector, then what is the value of lambda? So first, if A vector is perpendicular to B vector, means A dot B is equal to 0, as A vector is perpendicular to B vector, or theta is 90 degree and cos 90 is 0. So we have component is multiply lambda into 1 plus 2 into minus 3 plus 3 into 4 is equal to 0. So that is equal to lambda minus 6 plus 12 is equal to 0. So lambda plus 6 is equal to 0. So lambda is equal to minus 6. So this type of questions is asked. Next we come to the geometrical importance of scalar product. So A dot B is equal to AB cos theta, where theta is angle between A vector and B vector. So this is A vector, OB is B vector. Theta is angle between A vector and B vector. So if we draw a perpendicular BM, so OM is called scalar projection of B vector on A vector. So OM is called scalar projection of B vector on A vector, which is nothing but B cos theta. So that is equal to B cos theta. So B cos theta we can be represented as A dot B divided by magnitude of A. So B cos, because A dot B is equal to AB cos theta, so rather we can say either magnitude of A or A, simply A, that is A is a scalar quantity. So it's called scalar projection of B on A vector. Next we have vector projection. So vector projection is we simply multiply a vector quantity. Suppose it is A vector and unit vector along A vector is A cap. So next we have vector projection of B vector on A vector is equal to B cos theta into unit vector along A vector, that is A cap. So which is equal to A dot B divided by magnitude of A into A cap is nothing but A vector by magnitude of A. So, this is all about scalar projection and vector projection. So, we can take an example. It is scalar and vector projection. Suppose we are given two vectors, say A vector is equal to I cap plus j cap minus 3k cap, and B vector is equal to 2I cap plus 3j cap plus 4k cap. And so, what is this scalar and vector projection of A vector on B vector? So, we can draw a rough diagram. Suppose this is A vector and B vector, and so the angle is theta. So, scalar projection first, that is scalar projection of A vector on B vector is magnitude of A into cos theta, magnitude of A into cos theta. So, this quantity is A cos theta. So, which is equal to A dot B. We have A dot B is equal to AB cos theta. So, what will be A cos theta is called A dot B by magnitude of B. So, now A dot B we multiply component wise, so that is 1 into 2 plus 1 into 3 plus minus 3 into 4 divided by magnitude of B is nothing but root over of 2 square plus 3 square plus 4 square. So, which is on simplification is 3 plus 2 5 minus 12, that is minus 7 divided by root over of 29. So, this is scalar projection of A vector on B vector. Next we have vector projection of A vector on B vector. So, which is nothing but scalar projection of A vector on B vector. So, it is along B vector. So, that is along B vector we have a unit vector that is called B cap. B cap is a unit vector along B vector. So, it is B cap. So, which is nothing but minus 7 by root 29, and B cap is nothing but B vector divided by magnitude of B vector. So, which is minus 7 by root 29. So, B vector is 2I cap plus 3j cap plus 4k cap. Magnitude of B vector, already we have magnitude of B vector, that is root over of 29. So, which is equal to minus 7 by 29 2I cap plus 3j cap plus 4k cap. Next we have some more examples on dot product. So, suppose it is sum of two unit vectors is a unit vector. Prove magnitude of the differences root 3. So we can take three unit vectors, say A cap, B cap and C cap be 3 unit vectors. 3 unit vectors are A cap, B cap, C cap. Given that sum of 2 unit vectors is a unit vector, that is A cap plus B cap is equal to C cap. This is given. To prove that magnitude of A cap minus B cap is equal to root 3. So as A cap plus B cap is equal to C cap, we can square this both sides. So square means it is just a dot product, that is A square is nothing but A vector dot A vector, that is A square. So square means it is a dot product, so which is A cap whole square plus B cap whole square plus 2 A cap dot B cap is equal to C cap whole square. Now A cap is a unit vector, so its magnitude is 1, B cap is unit vector and C cap is again a unit vector, so each has magnitude 1. Now A cap square is 1, B cap square is 1, 2 A cap dot B cap is equal to 1. So 1 cancels out 1. So this implies 2 A cap dot B cap is equal to minus 1. Now again A cap minus B cap whole square. So it is a square means it is a dot product, that is equal to A cap square plus B cap square minus 2 A cap dot B cap. A cap square is 1, B cap square is 1 and we have 2 A cap dot B cap is equal to minus 1. So this is minus of minus 1. So this is equal to 2. So this implies A cap minus B cap magnitude is equal to root 3. So this is one important question, that is difference of 2 unit vectors is a unit vector. So we can take one more example. Some geometrical problems is also asked, that is semi circular angle is right angle. Proof by vector method. So we can prove whether is half circle angle is 90 degree. So we can take a circle, say O P B. This is A. O is the center and P angle is 90 degree. We can prove by vector method. So suppose this is A vector. So position vector A is A vector and B, say this is A, say this is B and this is A. Like position vector of A is A vector and B will be minus A vector because it is in opposite direction. So that is equal to minus A vector, or suppose this is B vector. Now this will be R vector. So we join like this to prove APB angle is equal to 90 degree. That is AP vector dot PB vector is equal to 0. Two vectors are perpendicular, their dot product is 0. So now suppose this is X vector, or this is X vector. So here this is R vector. So OP vector plus PA vector is equal to A vector. So OP vector is equal to R vector plus PA vector is equal to A vector. So PA vector is equal to A minus R vector. Similarly, we have PB vector. OB vector plus BP vector is equal to OP vector. OB vector is equal to B vector plus BP vector is equal to R vector. So BP vector is equal to R vector minus A vector. So now the AP vector dot PB vector. AP vector is equal to AP vector is equal to R minus PA vector, that is equal to R minus A vector. So that is equal to R minus A vector and PV vector is equal to OB plus BP. PB vector is equal to PB vector is equal to A minus R vector is equal to A minus R vector. B minus R minus B vector, that is PB vector is equal to B minus R vector, where B vector is equal to minus A vector. So that is equal to minus A vector minus R vector, that is minus of R plus A vector. So minus of R plus A vector. So which is equal to minus R square minus A square, as R vector magnitude is equal to A vector magnitude. So R square minus A square is equal to 0. So AP is perpendicular to PB vector. So P angle is equal to 90 degree. So semicircular angle is 90 degree.